Good afternoon. Can you hear me? Can you crank it up a little bit? It's St. Patrick's Day. Great. I'm not Irish. I do drink beer, though. Okay. Uh, okay. But the beer doesn't have to be necessarily green. Let's get right to it. Today we're going to talk about new stuff. The last time can I have your attention, please? I know it's St. Patrick's Day, but I hope you haven't drank already. Okay. They are not 21? Okay. Then don't drink at all, okay? I said it here in Cambonnet. I have to get that show on the road here. The last time we talked about chemical reactions, and when we do chemical reactions on the bench top, we do them at constant pressure because the pressure is constant with minor variations. It's 1 atmosphere generally, and this gives us the possibility to have a new state function, and that new state function is the enthalpy, and we measure the change of enthalpy, delta H, which is at constant pressure essentially the change of heat, the exchange of heat. And we have seen when we have a reaction where we have A moles of substance A and B moles of substance B that reacts to C moles of substance C and D moles of substance D. And if this reaction is releasing heat, then it's exothermic, and delta H is smaller than 0, because if heat release, Q is negative. And we can calculate essentially the heat that is released or the heat that we need to put in case of an endothermic reaction to make that reaction go. We can calculate this. And we calculate this from the standard enthalpy of formation of product A, reactant A, reactant B, product C, and product D. So you need to know these standard enthalpy of formation, and standard means we have this funny standard state, funny in quotation mark. We agreed to that the standard state, if you have solutions, it's all at 1 molar concentration, and if you have gases, it's all at 1 pressure atmosphere. Of course, you don't have it at 1 pressure atmosphere on the benchtop, the gas itself, but you're comparing just the products with the reactants. And really, it doesn't matter what state you have, as long as you have the same state, all right? And so how do we get the standard enthalpy of formations of A, B, C, and D of these compounds? You can look those up. They are tabulated. They are tabulated, and somebody has measured them. And so there's an agreement that the standard enthalpy of enthalpy of elements in standard state is 0. Or one can better say, not in standard state necessarily, in the most common state. For example, iron has the enthalpy of 0, iron metal. But iron doesn't come, and this is not necessarily the most stable state. Iron doesn't come as iron metal in nature, it comes as some iron ore. So it has reacted over the millennia with the surrounding and has formed pyrite or whatever metal that contains iron. So we have to extract that iron out of it. But for our purpose, so iron itself, we set as 0. And hydrogen, oxygen, and nitrogen, they are diatomic gases. And they are natural. Our oxygen here is O2. So we set this as 0. O2, standard enthalpy of formation or enthalpy of O2 is 0, okay? Of N2 is 0. Of, what else? Oxygen, nitrogen, what else do we have? Hydrogen is 0, H2. So now, if I want to determine the standard enthalpy of formation of 1 hydrogen atom, would it be positive or would it be negative? So hydrogen has 2 atoms. This is 0, the standard state. Now, what do I need to do in order to get 1 away? I have to break that bond. So how do I break a bond? I hit it with a hammer. okay, I have to put in energy to break that bond. And with this, that standard enthalpy of formation for H hydrogen gas will be a positive number. It will be this case here where it was a positive enthalpy of formation. So this will be positive. Hydrogen, oxygen, and nitrogen atomic gases, not molecular gases, atomic gases have positive enthalpy changes or enthalpy of formation. Now if you, for example, use water, hydrogen and oxygen react, hydrogen, H2 and O2, they're both 0. They react to water, H2O, and this has been measured, is minus 286 kilojoules per mole. And you've seen that, we did that here in class at the very first day. We let hydrogen and oxygen react with each other. We had these user explosions in the balloons, okay? So you see, so you can calculate now. You get these enthalpy of formations for those guys here, those individual reaction partners and the products. And what you do, you take the sum of the enthalpies of formation of the reactants minus the enthalpy of formation, the sum of the products. And the difference, if the difference is negative, then the reaction will be exothermic. If the difference is positive, then the reaction will be endothermic. If you have an exothermic reaction, we put a big shield here. The larger the number, the bigger the shield, okay? And because we need to calculate what the energy release or the energy need is in order to not endanger you. So the important point is that you have to have the stoichiometric factor, the number of moles. You have to multiply this enthalpy of formation with the number of moles in order to be correct, okay? So if you have here 2 moles, then you have twice the enthalpy of formation of A, for example. So today we're going to talk about calorimetry, and we talk about thermochemistry, and we have a little bit fun with food, F and F, okay? And but before I start with this, I want to briefly talk about heat capacity. You have done an experiment in the lab where you determined the heat capacity or the enthalpy of reaction or something like this by using a calorimeter, a bomb and an open calorimeter. And the heat capacity is the energy required to raise the temperature of an object by 1 degree. And it varies from material to material. So that's the ability of materials or of elements or of compounds to absorb heat. And if you have a large heat capacity, then it absorbs a lot of heat. If it's small heat capacity, it doesn't absorb a whole lot of heat, okay? And I will give you a little bit of example about this, one example please. So you can have a specific heat capacity, that is CS, there should be a little S there. This is in joule per Kelvin, and now it's per gram. This is 1 gram of substance is raised by 1 degree, and this signifies the energy that you need to do that. That's the heat capacity, the specific heat capacity. Now, if you know what substance you have, you can also have a molar heat capacity. So this is the energy that you need to heat 1 mole of substance up by 1 degree. So we have that heat capacity C, that would be CS, and this would be CM, that stands for molar, and this stands for specific. So the heat that you generate is Q, is the mass, times the heat capacity, times the change in temperature. You have done this. I think this was in your lab, and you must be familiar with this by now. So let's look at some heat capacities. Iron, for example, has a specific heat capacity of 0.45, and water, liquid water, has a specific heat capacity of 4.18 joules per gram per kilogram, okay? Now, if we divide this if we take a mole of this, then a mole of iron has a heat capacity of 25.1 joule per mole per Kelvin, and the degree should be gone here, should not be here, the degree sign, okay? And we just write Kelvin. And water has 75. So this is about, what would I say, iron is about, and this is about a factor of 3 here. If you go to molar, and the specific is even nearly a factor of 10 difference. So what does this mean? If you have a piece of iron, an iron rod, and you heat it up, that it's red glowing, all right? So you want to put this in a bucket of water. Let's say the bucket has maybe a gallon in there, all right? and this is a big piece, and it's red glowing. So you put this in the bucket, and then you take it out after it has cooled off, and you feel the temperature of the water. The water temperature hasn't risen that much, okay? That's the good part. That's how we cool, for example, iron. How you just, when you ever have seen a hoofsmith, how you call it, blacksmith, who puts horseshoes on the horses. How you call this guy? A farrier, thank you, a farrier, okay? Have you ever seen a farrier? He welds the horseshoe, and then he puts it in hot water, and he puts it on the horse, a little bit hot, still that it burns into the, I don't know what it's called, the material. The hoof material, I don't know, it's chitin actually, the material. Okay, so coming back to the iron that we cooled off in water, and so the temperature didn't rise. Water has a large heat capacity. Before the temperature goes up, it stores a lot of heat. Iron loses heat very easily because it doesn't have a high heat capacity. So you dunk it in there, and it cools off right away. All right, that's the meaning of heat capacity. If you, for example, have wood and concrete and glass compared with each other, and there you only have a specific heat capacity because you don't know the molecular mass of wood. There's no molecular mass of wood and no molecular mass of concrete and glass. These are all mixtures of things, or granite. And you see concrete, glass, and granite feels cold always, okay? Doesn't store so much heat. But wood feels nice and warm. So if you build a wood cabin or one of these log homes, and you insulate it very well from the outside, the inside will always feel nice and warm because it stores the heat so much, at least double as well as good as concrete or glass or granite. So wood is a very good building material, and with this you know now what heat capacity is and what you can do with it and what it really means. So you have used a calorimeter, a thermos in your lab, and this was a constant pressure calorimeter. It was open to the atmosphere. So there but there are other calorimeters. There are bomb calorimeters. Not that they are a bomb, but if there's too much going on, they could be like a bomb. But you close them, and you have your steel bomb, and you fill this with oxygen, and whatever you want to determine the heat capacity for, not the heat capacity, how much heat it gives off. And with this, you could know the caloric content. So if you want to, for example, determine how many calories 10 grams of yogurt have, you put in yogurt, okay? And you burn it, you ignite it here, the oxygen, you burn it, you see the temperature exchanges with this water bath here, the temperature will rise, you can measure that temperature, and around this you have it insulated, completely insulated, all right? So you did this, not quite like this, you had a bit different experiment. So since the energy is conserved, you have the heat of the reaction plus the heat of the bomb plus the heat of the water is 0, okay? So there must be something negative in there. That means the minus heat of the reaction is the heat of the bomb and the water, and now you know how you can calculate this here, and with this you get calories out of this. Yeah? And now we are with calories. We want to talk about food today and food calories. The first thing that you know, when you look at your yogurt, it says only 90 calories instead of 140, okay? Because they put some aspartame or something in there, or equal, so it's a little less fat. So it's 90 calories. You think, oh, that's great, it's hardly anything. No, that's the big C, okay? I used to say this in Spanish, the big C, but it's a different story, okay? I finally knew what it meant. So the big C means it's 1,000 physical calories. 1,000 calories. So if they say 140 calories, that yogurt, it's 140,000 calories, okay? Hang on to your seat, 140,000 calories. And they use the calories still. The calorie is not generally used in physics and chemistry anymore. It's the joule. We use the joule as the energy unit. And 1 calorie has about 4 joule. Of course, they want to hang on to calories because the number would be even 4 times larger they have to put in. So the yogurt has, and in Europe they do that actually, the yogurt doesn't have 140 calories, but it would be 4 times 4, 640 kilojoule, okay? 640,000 joule, yeah? So that's just one thing you need to know. So the food calorie is 1,000 calories as we know them, and one small calorie is 4.18 joule. And now power is essentially the energy that you use over time. And this is important for us because we're using our energy during the day. We have to constantly refuel to have our energy restored. And so this would be 1 watt is 1 joule per second. So you know a 100-watt light bulb, it uses 100 joule per second in energy. So these light bulbs, of course, they're not very efficient because most of the energy is given off as heat and very little is used to light your room. But now you have these fluorescent light bulbs, even the screw-in fluorescent ones, and you see it's 13 watts. That's an equivalent to a regular incandescent light bulb of 100 watt. So you save about you use 1/7 of the energy about, okay? So go home and replace your light bulbs. So 100 watts per day, what does this mean? The average grown-up human needs about 2,500 calories per day. If you put this in and you are moderately active, which very few of us are, you are moderately active, you will not gain any weight, you will sustain yourself very nicely, okay? So how much is that in joules? This is 2,500 times 1,000, so this is 2.5 million, and we need this in joule by 4. This is 10 million joules per day. That's what you need to sustain yourself, okay? Now, if we want to, and it comes out, in order just to function a little bit, we need about 100 watts every second, or 100 watts per day, okay? So that means 10 to the 7 joules per day. If you want to have 100 watts here, that's 10 to the 5th seconds. That's about the amount of seconds in a day. It's a little bit more than that, a little bit less than that. So it's 86,000 or something. And here I put 100,000 in. What this means, 10 to the 7 times 10 to minus 5, of course, divided. This should be divided, okay? Is 100 watts per day. You get then 100 watts per day. There's a little mistake in there. So you get 100 watts per day. This is what we need in order to, as you just sit here and you're quiet, you don't listen to me, and like this guy here, and he uses about 100 watts a day. His heart is going, and he's breathing. That's about 100 watts a day, okay? 100 watts just to maintain, to sustain your basic gradients, okay? So the brain has the function to get these gradients in there, that you have these chemical gradients, that you make your proteins, and you make your RNA, and you make all these things. That's about 100 watts, okay? So just to breathe and keep the brain full of blood, not much, but a little bit. And if you start thinking about Chem 1A, it goes up right away. It goes to 200, okay? And if you think very hard about this darn chem quiz, then it goes 3 times as much. You have 300 watts then at this time you need. And so 100 watts is about, if you walk very slowly, you don't walk like this. I never walk like this anyhow. 2 kilometers per hour is very slowly. If you walk normally, you use about you can do about 5 kilometers per hour. You don't have to strain yourself very much. So this is a very leisurely walk. That's like a walk when you have to go to class, but you don't want to. You barely go more backwards than forward, okay? Or nearly go more backwards than forward. This would be about 2 kilometers per hour. Or that would be 100 watts. Or at the 10% efficiency, this is a general efficiency of solar panels nowadays. They've gotten better. Now they make thin films. They got an efficiency of about 19%. But in general, a solar panel is between 10 and 13% at the moment. So if you have a solar panel of 1 square meter and you convert it to electricity, the heat, the sun, so at 10% efficiency, you get about 100 watts out of there, okay? So 100 joules per second. So let me talk to you a little bit about or ask you a question. Let me ask you a question. The specific heat capacity, we had this before, it was of water was 4.18 joules per Kelvin per gram. So we have it in calories, lower calories. It's 1 calorie per Kelvin per gram. And now I'm going to propose to you a new diet, okay? The new diet is if we drink cold water, the cold water comes out of the tap, it's about 12 degrees Celsius. Your body is about 37 degrees Celsius. The delta T between this, when you put the water in your body, is 25 degrees. So it has to raise the temperature by 25 degrees to get it back into your body temperature, all right? And so you could do that new diet, you drink a lot of cold water, okay? And just from heating it up in your body, I'm not proposing this, okay? Just from heating this up in your body, you would be able to lose some weight. I don't know if you're able to lose some weight. That's what we're going to find out. So this is your daily intake here, and that's what you would need to lose about, that you stay plus minus 0, and if you don't eat less, then you start losing weight. So if you want to lose 2,500 calories, how many glasses of water would you have to drink? 1, 20, or 500? The water is about 200 milliliters. The density is 1, as you know, and the delta T is 25. Why don't you think about this and give me your answer? So that's the calorimetric formula. That's exactly what you need. I talked about that. That's why I talked about it a little bit. What's M? What's C? What's delta T? I think you should be able to put this in. I would give it for 1 glass of water. So the people who wear green, are they actually Irish? No, huh? Everybody's Irish on St. Patrick's Day. Okay, I'm going to be Irish then. Actually, the people are not green, they wear green. Let's see how the diet works out for us here. Okay, you say 1 glass, of course, doesn't do it, because I drink a glass of water a day. It doesn't look like I'm losing weight, okay? 20 glasses might work. Others say 500 glasses. So what do you think? Discuss it with each other. All you have to do is calculate. It's very, very simple. Have a discussion. What do you have? Okay. Well, I agree with you, with C, okay? Okay, that would be a great diet. I don't recommend it because one thing to lose weight is that you drink so much water that you flush out all your electrolytes, okay? You die, okay? Not a good diet, but you definitely lose weight, okay? The other point is if you drink that much water, you have to go to the bathroom all the time. You're running back and forth and back and forth. You lose a lot of weight by doing this, okay? So not even with only 500 glasses, you can last maybe 30 glasses a day. It's already too much, though. I'm not recommending it, okay? Not that I get sued here. So our calorimetric formula was this here, 200 grams. Delta T is 25 degrees. Doesn't matter if Kelvin or Celsius. But 1 calorie per gram, that's the specific heat capacity. That's the heat capacity, specific heat. So there's 5,000 chemical calories or 5 large calories. So now how often do you have to do 5,000 divided by 5? That's your 500 classes, okay? And with this, the answer was 500. So where did I get the 200 grams? 200 milliliters. There it is. Density of water is 1. 200 milliliters is 200 grams, okay? Oh my gosh, okay? All right. So now let's talk about our metabolism. So we eat carbohydrates, we breathe in oxygen, and we breathe out CO2 and water. You can see your breath in a cold day, not here in this area, but if you go in a colder climate, you can see the water condensing as you breathe out. So essentially, you eat and you breathe a certain amount of food and breathe in oxygen and breathe out CO2 and water. And so at the beginning, you were at this energy. At the end, this is this energy, okay? Or this maybe. And so actually it doesn't matter. This is why we defined this wonderful state function. It doesn't matter if there's about 1,000 reactions or 10,000 reactions in your body going on, that this happens in your brain and everywhere are reactions going on, that you at the end come out with CO2 and water. At the beginning, you have your food. At the end, CO2 and water. The difference is what you have used up in energy or what you gained in energy. Okay? So this is how we can look at our caloric intake. And we look, for example, sugar has 4,000 calories per gram. Okay? A pound of sugar, 1 pound is 454 grams. A pound of sugar is about 1,800 or 1,800 large calories per pound. 1,800 large calories. Now, fat is much denser, okay? And fat has 9 calories per grams. This is about 4,000 nutritional calories per pound of fat. Every pound of fat is 4,000 calories. You want to lose a pound of fat, you have to work off 4,000 calories. Or you don't eat for 2 days. Don't do that, please, okay? But this would be a pound of fat. So if you listen I don't know if you sometimes watch television at night. I do this quite frequently, unfortunately. And so I see these guys, they say, lose 10 pounds in 3 days. Okay? That's not possible. Not possible. So it's all a lie, okay? You have to work very hard to lose weight, and you have to have the right nutrition to lose enough weight. So now that's why we're storing our fat as our energy reserve. So can you imagine if we would store sugar instead? I would have a ring of sugar around here, okay? It would be about double the size than the ring of fat I have, all right? So that's why sugar is not a good way to store energy. That's why we store it in fat, and that's why we look like we do, okay? And so if we look at these Snicker bites, you know these Snicker bites here? They are delicious little morsels here. And let me get some of them. These Snicker bites, they are the itsy bitsy teeny weeny, I can't throw that far. Teeny weeny Snicker bites. You know how much calories there are? Large calories. They are, gotta come down here. They are, it says about 170 per serving. Serving size 4 pieces. So this is about 45 calories. Let's say 50 calories. 50,000 calories. Okay? This little Snicker bite, have one, please. I'm sorry. Okay, like some too? Okay, I do the best I can here. Let's see. The guy behind you gets it. Let's do a couple of those. Oh, my throwing is not so good today. Marshmallows is better. Come on, catch it. All right. No, I can't throw that far. Okay, all right. So this would be, if you are sort of a first semester student, fresh coming from home, the laundry isn't done and you don't know how to cook food or anything. So that would be a perfect diet. You eat 50 of those a day, you get 2,500 large calories. So that would be the Snickerbite diet. You would sustain yourself, but you wouldn't live very healthily. You wouldn't be able to do this for a long time. Now, the other thing is you could do the donut diet. That's even better. Lots of us do this. And so a donut has 400,000 calories, or you would need then 6 a day to maintain yourself at the 100 watt. So that's the donut diet. I don't recommend it, but I know some people who do that at times. Or the pizza diet, for example. I don't have the number for pizza here. It's much, much higher. So that is how you would gain calories. And you now have here, this is, for example, sugar has 1,274, sucrose 1,274 kilojoules per mole, standard enthalpy of formation. Remember iron oxide and aluminum oxide? We did the last time. The difference was released in energy. It was so much energy released that we melted the iron oxide and the iron dropped out of the reaction vessel. So remember, let's see, you needed about 2 kilometers per hour. You have to go to use about 100 watts, okay, or 100 joules per second. So how many Snickerbites are required to fuel a 1 kilometer walk? So you're more or less crawling, essentially. Is this 1 Snickerbite, 10 Snickerbites, or 100 Snickerbites? Why don't you give me a quick answer? That's like from here to Clark Kerr campus. Anybody lives there at Clark Kerr? Okay. So you can have an extra Snickerbite if you walk over there. But some people I know, they take the bus, actually. I've seen it. Actually, I did give you the answer already, huh? While I was talking about Clark Kerr campus. Okay, 10 is not right. Gee, that would be great. You just walk a kilometer and then you can eat 10 Snickerbites. No, actually it's 1, and I'm a little bit in a hurry because I have some other nice experiment here for you, a couple of those. And I'm going to resolve this for you. You need 50 calories is 1 Snickerbite. So there's 50 times 1,000. So this is times 4 is 200,000 joules, okay? All right, 200,000 joules. And 1 kilometer is 2 kilometers an hour. You need half an hour, that's 1,800 seconds, okay? 100 watt times 1,800 seconds is 180,000 joules, okay? That means 180,000, so this is 200,000 joules, and this is 180,000 joules, so that's about the amount that you need one Snickerbite, okay? You still have to walk a little further, actually, okay? And one bite is about a half an hour at 100 watts, so slow walking, very slow walking. And this was the answer. Now, I need a volunteer, please, because I have a question, and I need a hungry volunteer, hungry and strong. I have, come on, please, come on down. You get a donut from me. So, what's your name?
Ali?
Ali?
Yeah.
Nice to meet you, Ali.
Hi.
Are you allowed to eat donuts? For your parents?
I'm on a diet, but
I
I can eat it, yeah.
Donut diet?
Yeah.
Okay, good. All right. So what I would like you to do is, you're going to eat that donut. Bring your eye clicker. Or can you click for him at the eye clicker? Where has the eye? Just click for him, okay? That he doesn't get punished coming down here. So I have this dynamo here, okay? And this dynamo is about, if you crank it hard very quickly, so it's not 100 watt really, but let's assume it's a 100 watt bulb, okay? And you crank that here, and you eat that donut and keep cranking to expand that energy that you're eating, okay? Please enjoy the donut and crank here to keep the...
I crank and eat?
Yeah, you crank and eat. Okay, please, sir. Ali. Okay? Goes this direction. You don't need a... you're planning to stab yourself in the eye accidentally?
No.
With the donut? No, okay. Good. All right, so you crank. Enjoy.
Okay.
Good. So now here's my question. For what period can a 100 watt dynamo, that's him here, go ahead, eat. Be driven. Take your time though. But be driven after the consumption of one donut to be equal, okay? Does he do this for 1 second, 1 minute, for minutes, or does he have to do this for hours to expend all these calories or the calories that he's taking in? Why don't you think about this and give me your answer? He's slowing down already? Is it good, the donut? Only 2 days old. No, just kidding, okay. Just kidding. It's 3 days old. Okay, you're doing good. You're very good. You're a good sport, Ali. Thank you. Thank you for helping me. So, what do you think? A couple of seconds we send him away, or a couple of minutes, or I give him another donut in case. Hours, you think? Hours, okay. Seriously, I don't have anything to drink here. That's it. Okay, good. So come on. That's 2020. No, it's okay, Ali. He's doing a great job. How's the eating coming? Yeah, good. He eats faster than he cranks. Good. So, but he said he is on a diet, so he's going to expend all his energy, and I really appreciate it. It's very hard, isn't it? Wow, he ate the donut already. He's a speed eater. Give Ali a hand. Thank you very much, Ali. I appreciate it. Thank you. Okay. So, the answer. What's the answer? If you can turn down the light a little bit, that they can see the screen a little better. Thank you. And the answer is what? Yes, the answer is ours. Of course, it's ours. Where's my? There it is. C. Okay. And let's see how we calculated that. You guessed it, didn't you? You guessed. Sure. So, how many hours would he have to crank the darn thing? That's the question, okay? So he has 400 calories is 1,600 times 10 to the 3 joule. We established that already. Okay? 1 watt is 1 joule per second. 1,600 times 10 to the 3 joule is, in order to get 100 watts, we have to divide it by 16 times 10 to the 3 seconds, okay? And 16 times 10 to the 3 seconds divided by 3,600 seconds per hour is 4.4 hours, okay? You are lucky that you didn't have to do 4.4 hours, but you do all the running afterwards, okay? The answer was 1 donut about 4 hours at 100 watts, but he used more than 100 watts. He was cranking very hard. You could see him sweat, so he used probably 300 watts. So he might get away with 2 hours or something like this, okay? Good, so you understand now. Now, I would like you to compare the heat released in the following reaction. This was obviously the oxidation of sucrose to CO2 and water. And the numbers that you need are here, okay? And the other reaction we did the other day, you remember that it was an exothermic reaction. It was the thermite reaction. We had a mixture of iron oxide and aluminum, and we got out molten iron and a lot of energy released in addition to this. Can you remember how much the energy was about that we released? That was the difference between these two here, okay? That was about 840 or 852 kilojoules, something like this, yeah? Minus 852 kilojoules. So we have established this is minus 852 kilojoules, okay? So now I want to know from you, what's this here? And you compare this to this here then. And would the thermite reaction release more energy than the combustion of the oxidation of sucrose, number one? Or would sucrose oxidation release more energy than the thermite reaction? Remember the thermite reaction? So, or is it the same? Okay, or definitely the thermite reaction will release more energy than the sucrose oxidation. Why don't you think about it and give me your answer? It's a calculation, and I would suggest that you approximate. If you need, for example, oxygen is obviously zero, the standard enthalpy of formation, is it? CO2, the standard enthalpy of formation is about minus 400. Water is about minus 300. Sucrose is about minus 12 or 1300, whatever you prefer. Or you just fill it in, put the stoichiometric factors in, and calculate it. You got to have this right. Okay, let's get started. So you have to calculate the energy of that reaction. Product, sum of enthalpy of products, minus the sum of the enthalpy of formation. The sum of the enthalpy of formation of the reactants. Can you hear me in the back? Switch it there? Good, okay. But Henry sits down here today. Didn't hear me. So you got to look up there. But you can see all this, that's important. So there is obviously an ambivalence here. One say it's either the thermite, you have seen it, how much energy was released. The other said he wouldn't ask us if that would be not maybe the sucrose oxidation would release more energy. Why don't you discuss this with each other and give me a new revised answer, some of you at least? You see that shielding is bigger than the thermite reaction shielding. Remember that? Maybe that gives you an answer. Yeah, the math would be another possibility. Are we clear? You got an answer? The right one? You actually can calculate this. I think you do this at your in your homework at the moment. Okay, there is a slight majority for A, and I go with A. Why is that? So this is our equation. We calculate the heat of the enthalpy of formation of this here. This means liquid here. So this is delta H of reaction at standard state is the sum of the heat of formation of the products, that those guys, minus the sum of the heat of formation of the reactants. These are these guys. So we have 6 CO2. This is 6 times CO2 is about 400. 6 times minus 400 is 2,400. Then we have water, 6 times 300, about 6 times minus 3, 2,400, 4,400, 1,800, 4,200, that's 4,200. And then we take minus, and this was about 1,200, minus 1,200. So I had 2,200 minus 1,200 is plus 1,200. 4,200 plus 1,200, minus 4,200 plus 1,200 must be minus 3,000. That must be minus 3,000 kilojoules per mole, okay? And this is about 4 calories, large calories, per gram of donut, all right? So why don't we have a look at this? And we do our oxygen oxidation with liquid oxygen. We have liquid oxygen, and if we could show, you see the donut hole, a tiny, tiny little hole of donut. And Karen will now heat it up to get it, the activation energy going. There it goes. The red glowing donut. That's the energy in the little donut hole, okay? And you put those in your mouth. It goes and goes and goes and goes. Compared it to the thermite. It's 4 times as much energy than the thermite about. One teeny weeny little donut hole. Okay. It's still going. It's like the Energizer Bunny. There it is. Isn't that unbelievable? How much food has in energy stored? Okay, I see you on Friday. Happy St. Patrick's Day. Huh? Liquid nitrogen and liquid oxygen. Liquid oxygen. We always do liquid oxygen.